alkanes. So alkanes have a general formula of CnH2n plus 2. They are saturated, meaning they contain single bonds only of carbon. As you can see, single bonds, and they're saturated completely with hydrogen. This counts for both alkanes and cycloalkanes. Alkanes can be used as fuels. This is often seen in fractional distillation, which you may have come across one of these towers before, perhaps in GCSE. And effectively, the heated crude oil is placed at the bottom of the tank, and at the bottom there is a high temperature, and at the top there is a low temperature. So it can be separated into fractions by distillation due to the boiling points difference to produce different fuels. So at the top here we have short chain alkanes and long chains down here. So the way this works is, so the properties at the top would be there's low boiling point, they burn readily, burn with a clean flame, they're light coloured, they're more sort of runny, and yeah, they're short chains. And at the bottom we'll have the high boiling point, less likely to burn, probably darker in colour, and longer molecules. So what happens is we have this vaporized crude oil coming at the bottom, at the base of the column. So this is because this temperature is lower than the boiling point of the largest molecules. They liquefy or solidify as tar. And it's tapped off the bottom. So others remain as vapors, and so they rise up to the next layer, and this layer will be a bit cooler than the previous bit below, and therefore they pass through these bubble traps and condense, and as they condense they can be taken away and at their different points. So longer molecules may remain as a liquid, and shorter revaporize and rise up to the next cooler layer. So each of them are, as you can see, they've all been drawn off because, say, let's take petrol for example. So petrol, because it's got a low boiling point, it's able to, it's boiled here, and it rises up as it's gaseous. Still gaseous, it's got a lower boiling point than that, still lower, and at 40 degrees it will become a liquid and be run off there. So as I mentioned before, there's these things called bubble caps, which are sort of in between, they're on the fractions, and they're really clever at allowing these different types of fuels to be drawn off at it. So all these vapors rise up from each layer. Remember, this would be a cooler layer, this would be a hotter layer, and they rise up and they go through here and they go to the top, and then they condense, and then those, so ones that will have that at this point here, they will just condense and be drawn off, whereas others with a lower boiling point will be able to still vaporize and go into a gaseous form and raise up to the next level. So two problems of fractional distillation. Fractions cannot be used directly, as they must remove the sulfur compounds first, and the demand for lighter chains outstrips the output of the column, because obviously they'll be throughout the whole thing, whereas we prefer lighter chains and smaller chains. So to combat this problem, we have something called cracking. And cracking is basically the breakdown of molecules into shorter chain ones by heating with a catalyst. So effectively what we have is a reactor where we're putting in our feedstock and our steam here, and so this is where the cracking actually takes place. And so then we have here our stripping stream, and our cracked products come out, and effectively what happens here, all this stuff, is our catalyst regenerator. And what we're doing is we clean the catalyst, and it can come all the way back round and it can be used again. which is very useful. So, for example, cracking, you'd get from this longer chain to two smaller. So we've got decane here, which has got 10 carbon atoms, and which is broken down into octane, 8, and ethene, which is obviously an alkene molecule with 2 carbons. So reforming is the process of straight chain hydrocarbons into branch chain alkanes and cyclic hydrocarbons. So this is because they burn way more efficiently, and that's because they can rapid combustion. So the example of this would be pentane going to cyclopentane. Obviously, you're losing 2 hydrogens though. So, excuse my bad drawings. So you've got pentane here, 1, 2, 3, 4, 5. And that will get us to cyclopentane. And then you've got your 2 hydrogens. So pollutants formed from fuels are carbon monoxide, oxides of nitrogen, oxides of sulfur, carbon particulates, and any unburned hydrocarbons. So problems from these pollutants is obviously you've got the toxicity of carbon monoxide and the acidity of oxides of nitrogen and sulfur. So one way we try and get around this is we have catalytic converters, fitted to cars. So this solves some of the problems caused by those pollutants that we mentioned earlier. So the reactions that go on is the oxidation of carbon monoxide to carbon dioxide. So you obviously add oxygen. And oxidation of unburnt hydrocarbons. So, for example, you've got octane here as an unburnt hydrocarbon, and that just makes CO2 and water. And then nitrogen dioxide and carbon monoxide are put together, and they make just nitrogen gas and CO2. So obviously, so you've got these bad gases here, and these are still bad gases, well, apart from nitrogen and water, but obviously they're a lot less bad for the environment. So it's really helpful to be able to have these fitted to cars because it helps to remove some of the pollutants at least. So they use thin layers of expensive materials to increase the surface area. These are often expensive ones, like platinum I think is used. So we can also use alternative fuels. So that's biodiesels and alcohols from renewable sources. And you need to be able to compare these to non-renewable fossil fuels that we talked about. So moving on to the chemical reactions of the alkanes. They do many chemical reactions. Let's go into it. So combustion, or with oxygen, obviously. So it can either be complete combustion, whereas in the alkane will produce carbon dioxide and water upon combustion with oxygen. And always remember to balance the equation, which is a good note. And then also you have incomplete, where there's obviously a lack of oxygen, so there'll be less oxygen than you'll be seeing in the complete equation. And that will either make carbon or carbon monoxide, and then you still get your produce of carbon dioxide and water. So with a halogen, so the mechanism is free radical homolytic substitution. So what does this exactly mean? So a free radical is a species with an unpaired electron. It's highly reactive, and it's represented by a dot. So you'll see that later. So it's also homolytic, so it's the breaking of a covalent bond, so the electrons are shared equally. And it's also a substitution reaction, where an atom or group of atoms replaces another. So remember, in a mechanism, a curly arrow with both these bits here means that you've got the movement of 2 electrons, or a pair of electrons, as opposed to here, which only shows the movement of 1 electron. So, for example, let's take this one here, and the 3 steps to this reaction is initiation, propagation, and termination. So let's start with initiation. So let's go for just a normal black. So the first things first, so we've got our, let's just write the equation up here quickly. I've completely forgotten what it is. Oh, yeah, one more. So as you can see, this group here has lost one hydrogen and you replaced it into a chlorine here. So that's the substitution part, obviously. So the first step is the initiation, and what you need for this is UV light. It's very important. I don't know why it's joining up the dots. It's a bit random. Okay, oh, oops. Right. So the first step is, so if we take our molecule of chlorine here, so what we have is the movement of one electron from this bond into this chlorine, one electron into this one. Make sure, remember, signs from earlier. And this is done by UV light. So I'll just make a note of that. And that makes our chlorine free radical and another one too. So as you can see here, so this electron, so imagine one electron moving to here, and effectively that's made our free radical here. This is our free radical. So because it's an unpaired electron, it's going to be very reactive. So next step is propagation. So effectively what we can take is our, so let's take our molecule of butane, so effectively what happens here is, so because this chlorine molecule here is, this free radical is highly reactive, what you can do is effectively this bond here can be broken. So what we can do is move the electrons, so one electron into here, and then the other one can pop out to here, and that can form a bond. And that's going to make us another free radical. Just write it down here so we've got enough space to see. Because now this species has our one unpaired electron here as it's moved from this bond here. And then obviously we've got this and this one here, so obviously we're going to make a remaining product, which is HCl. So, but obviously we've got a free radical here. This is our free radical. Like that triangle around it. So what we've gone for from our free radical is that that's obviously going to react with our first reagent, which will be chlorine. So there's a second step to propagation, and let's just draw out our product that we just got. Oops. That's not that. Actually, that's it. Oops, it was butane, wasn't it? Right, so we've got our free radical here, and we've got our molecule of chlorine, which is obviously diatomic. So we're going to take this unpaired electron and one electron from this bond, and that is going to make us a bond here, which is going to show us our substituted chlorine group from here. And that's also going to produce, because this one's left here, and we can imagine that all we've got is one electron from here, and this chlorine, and then we're also going to make another free radical. So this reaction in this stage here can go on for a long time, because obviously you have another free radical. So this free radical can react again, and that can substitute off another group of another hydrogen until there's no more. So in order to stop this reaction, we have a termination step. So in termination, the only way to stop having a free radical produced is to have a free radical react with a free radical. So let's take one of the free radicals that would be in a reaction mixture. Oops. There we go. Sorry, glitched out a bit, just to forget those. And then we can also take our free radical here. And these can react together with this unpaired electron here, with this unpaired electron here, and that forms us imagine that with hydrogen around it, our product, but with a chlorine group substituted in. Remember, here there will be no free radical, so no dot. So the limitations of the use of radical substitution when synthesizing organic molecules is that there might be further substitution reactions, because obviously, as I said earlier, it can, because the production of another free radical, that free radical can go back and react with another reagent. And also it requires UV light for that first initiation step.